In this session, we talk about the solution of ODE. This is what I will call this step 5 of this 5-step modeling exercise. So if you recall, at the end of step 4, we come up with this differential equation as linear ODE in terms of the deviational form of the variable. Now step 5 is the solution of this equation. So if we are given the information that suppose the level was at some value, so if we take t equals 0, so if we plot the level, that is h, it was initially at some value, whatever the value it is, and I want to see what will be the level if a change is made in the flow. So whatever the value of flow was, again at this time, we'll consider some scenario. If the flow is changed, say from whatever initially it's from 10, if it goes to 12 or something like that, so there is a change of 2 here. So if you recall, the value of the function at the deviational form will be then 2 delta naught. Okay, now to find out what will be the value of this level in terms of its deviational form. Okay, now that's the purpose of this exercise. So in the first step, we'll take at in the what if we call it step 5.1. So take Laplace transformation. So if we take the Laplace transformation on both sides of this equation, we'll have tau So now from this property that Laplace transformation of a constant times a function AFS, also using the property that if the Laplace transformation of a function ft equals fs, then the Laplace transformation of the derivative of the function become fs when the value of the function at time 0 equals 0. So if this is 0, then we'll have only this term. So if we take the Laplace transform of this, now what we get is that the left hand side will have tau out s, if I write h prime s plus k prime s. Typically, we'll use the notation if the function is represented as the small letter. We'll use in the Laplace domain the capital letter of the to represent the same function in the Laplace domain. So if you rearrange this, we'll have h prime s equals Now for this case, suppose you have taken the example that this f prime t equals 2 delta naught. So f prime s will be 2 over s. Okay. So we'll have h prime s will be now if we take for a general value, if f prime s is equal something like m over s. So the magnitude of the change in the input is m. So we'll have a general formulation. S. Okay. Now this is the expression for the output in the Laplace domain. So then step 5.2 will be some sort of rearrangement of the equation. So what I mean by rearrangement is that if we don't know the, because next step is to inverse this to get the function back in the time domain. So if we do not know this term, what is the inverse Laplace of this entire term, we use the what is this so-called partial fraction expansion to express it in terms of the function that we know. What I mean by is that on the right hand side, suppose I write it as km over s tau s plus 1. If I don't know the inverse Laplace of this, I'll try to use partial fraction to express it something like c1 over s plus c2 over tau s plus 1. Then using the methods with then using the procedure for partial fraction expansion, we can find the values of c1 and c2. For doing that, we'll just simply take this to be, to get this partial fraction expansion, we can write this equals c1 tau s plus 1 plus c2 s, putting x equals 0, we'll get km will be c1, and then equating the coefficients of s. You can get on the left hand side there is nothing s, so this will be c1 tau plus c2. This will give us c2 equals negative km tau. C2 equals negative c1 tau, or c1 equals km, so negative km tau. Okay. So now we get this h over s will be simply c1 over s, meaning km over s minus km tau over tau s plus 1. So I write it as km over tau, sorry, km over s minus km over s plus 1 over tau. Okay. Now take the Laplace inverse. So we take the Laplace inverse here. So the Laplace inverse h over s will be Laplace inverse km over s minus Laplace inverse km over s plus 1 over tau. So if I write it as the function in the time domain h prime t will be, km is a constant that comes out, so Laplace inverse 1 over s becomes just simply 1. So this term will become km. So Laplace inverse km over s is km, because Laplace inverse of a constant over s is the value of the constant, minus again this km term can come out, and Laplace inverse 1 over s plus a equals simply e to the power negative at. So t and a equals for tau. So we get here h prime t equals km 1 minus negative t over tau. So that's the solution of this differential equation for the value of f prime t to be some value of m delta naught. Okay, so we use the f prime t, for this case equals m delta naught. Okay, so remember this equation, we'll be using the equation lots of time because it's the general formulation of the solution of a first order differential equation.